Okay, we were discussing the Wiener filter. So we have defined the problem statement in a Wiener filter like this, that given an input sequence un to a discrete time linear filter with some filter weights W0, W1, W2 and so on. So this filter, it produces the output yn, and then you had a desired response sequence dn, and you compute the error sequence by finding the difference between dn and yn. Okay, so the problem statement in the Wiener filter was to design a filter or to select the filter weights in such a way so that this error is minimized in the mean square sense. Okay, so for that we have taken a gradient cost function which was the mean square error, and then by applying some gradient operator, this we have equated equal to 0. And in the first instance we have got a principle which was called as the principle of orthogonality, so which states that at the point where the filter operates in the optimum condition, the input samples and the error sequence, they are orthogonal to each other. Okay, and then we have further expanded this equation and we have got a solution for the Wiener filter which we called as Wiener-Hoff equations, so which was W optimum is equal to R inverse P. Okay, so where R is the autocorrelation matrix of the input sequence and P is the cross correlation matrix between the input and the desired response. Okay, this is what we have discussed so far in the Wiener filter. So we will look to Wiener filter, or in fact we will derive these Wiener-Hoff equations with a different perspective. What we have stated in the early, that when you choose this cost function for this Wiener filter J, we have chosen this cost function as the minimum or the mean square error, okay, which was expectation of mod n square. And the reason for this was that since J of this cost function, it is a second order dependence on the filter weights. Okay, so as a result of which you get a m dimensional surface which has a unique minima which gives basically the optimum point. Okay, so this you can see that how this J function will be second order dependence on the filter weights. So for that we will try to find its error performance surface. Okay, so we'll see the dependence of J on the filter weights, and if you plot it you'll get a m dimensional bowl type surface. Okay, so for that again we see J, which is E of mod n square. You can take it as expectation of En into En conjugate, and En is the difference between Dn and Yn, and Yn was your Wk star into Un minus k. So if it is having a finite length filter, so k will go from 0 to -1. So accordingly your En star will become Dn star minus Wk into Un minus k star. So k from 0 to -1. Okay, So if you expand like this, if you put these equations of En and En star here, you will get dn minus summation of wk star un minus k as one term, summation over k, multiplied with En star, which is dn star minus wk un minus k star, again k from 0 to minus 1. Okay. So if you expand these terms, you'll get four terms. First you'll get dn into dn star, then its expectation. Okay, so you'll get expected value of you'll get mod dn square. Okay, dn into dn conjugate, it will become mod dn square and its expected value. Then dn multiplied with this sequence and e operator applied on that product. So you can take e inside the summation and you can write it as summation over k wk into e of u of n minus k star into dn. Okay, then you multiply this term with dn star, again take its expectation, and if you take this expectation inside this summation, you will again get this term as wk star into u of minus k into dn star. Okay, and the last term you will get, if you multiply these two terms, you will get double summation. Okay, so let us suppose I take one summation over k and one over I just to differentiate. So summation over k, summation over I, this will become wk star into wi. For this case I am using index I, and e of u of n minus k into u of n minus I star. Okay, this is what is cost function j. And if you look to this j, so e of mod n square, this is nothing but the variance of, so I can write it as sigma d square, variance of the sequence tn, assuming it that has a 0 mean value. Okay, minus summation of wk into this. If you see to this term first, it is summation over k wk star. Now e of u of n minus k into dn star, it is the correlation between un and dn at a lag of minus k, because it is n minus k minus n, so you'll get p of minus k here, so into p of minus k. Okay, and then minus wk, now this will become p of minus k conjugate, because if you see to this term, this is the conjugate of this, so this is minus p, this will become p of minus k star, so minus wk into p of minus k conjugate, and last will be plus summation of double summation over k and I wk star into wi. This will become autocorrelation now, sequence at a lag of I minus k. Okay, this is what is my cost function, and you can see here now that this cost function j is the second order dependence on this filter coefficients or filter weights, because we are wk into wi. Okay, so when k and I becomes equal, it will become square. Okay, otherwise in one case is wk it may be, or if wk and wi they are not, if k is not equal to I, in that case it is a constant maybe, but if k and I are same, so it becomes second order dependence. Okay, so this j function is a second order dependence on the filter weights. Accordingly, if it has m variables and if you plot this function j with respect to m in n dimensional space, so it will be a shape like this. For the second order dependence, it is a ball-like shape which has a unique minima. Okay, so that unique minima is the optimum point or the Wiener filter solution. So again, if you apply the gradient on this j del j and you equate it to 0, you will get the same equations which we have got earlier, which is Wiener equation. Okay, because you want to apply gradient on this, so this becomes, the derivative of this becomes 0, it is constant, and the derivative of this with respect to the del operator is again del by del ak plus j del by del bk. Okay, so wk star you have to write it as ak minus jbk. So since you are differentiating with respect to wk in this case directly, so it will become just p of minus k this term. Okay, similarly here it will become p of minus k. Okay, so p of minus k and minus p of k will become minus twice of p of minus k. Okay, so you have to find this again, the gradient vector del j, which is the vector with respect to ak and then with respect to bk. Okay, like that. So that you already know, that we have discussed already, and you have to equate this gradient equal to 0 for all the values of, for all the differentiators. Okay, so if you do this differentiation again, and in this part if you differentiate with respect to k wk, so you will get here twice of summation of wi r of I minus k. Okay, why this factor of 2 here? Because see, when k becomes equal to I, okay, if in this series if k is not equal to I, I will be taken as a constant, so wi into r of I minus k, and the derivative of wk with respect to wk, it will become 1. Okay, but at the point where k becomes equal to I, it will become wi square. Okay, so derivative of that or wk square with respect to k, so it will become 2 into wk. Okay, like this. So that is why getting this term to here, and then if you equate this to 0, you can get the same equations, that summation of wi or I minus k is equal to p of minus k, which is one of equations, or you can put them in the matrix form, in more compact form, w is equal to r inverse p. Okay, so we have shown here that how this cost function j, which is the mean square error, it is a, this function is a, depends upon the, it is a quadratic function of the filter weights or filter types. So you have a m dimensional in general surface which is called as error performance surface, and that surface has a unique minima, which is the Wiener filter solution, or which is given by Wiener-Hoff equations. Okay, so when you apply the gradient and you find the partial derivative with respect to all the filter coefficients and equate to 0, you basically directly find this point, which is the Wiener filter solution. Okay, and then you will see that what will be the minimum mean square error, because we are trying to, in all these cases we are trying to minimize the minimum mean square error, and when you have minimized this mean square error, what will be the minimum value of that? Okay, so when the filter operates in the optimum sense, in that case this error sequence, which is given by dn minus y naught n. Okay, so y naught n is the output of the optimum filter, y0n or y0n in fact it is. Okay, it means at the point when the filter gives a minimum mean square error, at that point the output is denoted by y0n and e naught n is the error in that case. Okay, And you will see that in general, when the filter operates in the optimum sense, it means the output of the filter yn is a very close estimate of the desired response dn. Okay, so these are my filter weights. So when the filter operates in the optimum sense, in that case that it is minimum in the mean square sense, it means yn is a very close estimate of the desired response. So yn not yon optimum output I have placed with d cap n, where d cap n is the estimate of this desired response dn. Okay, or you can say that your dn can be written as e naught n plus d cap n. Okay, now if j minimum, let us suppose j is the mean square error and j minimum denotes the mean square error of this final filter, then it will be given by e of mod e naught n square. Okay, because e naught n is the error when the filter operates in the optimum sense. It means when the mean square is minimum. So if you find its expectation on the mean square value of this, that will be the minimum mean square error, j minimum. Okay, so if from this equation, if you find the mean square value on the both sides, so mean square value of dn, it will give the variance of d, which is sigma d square, assuming that is headed 0 mean value, and the mean square value of this is nothing but the minimum mean square error and plus sigma d cap square. Okay, so or you can say that j minimum is sigma d square minus sigma d cap square. Okay, so the minimum mean square error of the oneness filter is basically nothing but the difference between the variance of the desired response and the estimate. Okay, so you find the variance of the desired response and the variance of this output sequence. So the difference between these two variances is the minimum mean square value. Okay, or since if it is assumed to be zero mean process, so this variance is basically the power in the signal and this is the power in the signal. Okay, so the difference between these two powers, that gives you the minimum value of the mean square error, or you can normalize it to make it a variable which lies between 0 and 1. So if you divide this with sigma d square on both sides, you will get j minimum upon sigma d square as 1 minus sigma d cap square divided by sigma d square. Okay, so this I can take and write as epsilon. So epsilon is 1 minus sigma d cap square upon sigma d square. This is called as the normalized mean square error. Okay, and its value will always be between 0 and 1. Okay, because see from this equation you can see that j minimum upon sigma d square. So j minimum is the minimum mean square value, basically power. This is the power in the desired response. So power, it cannot be negative. So as a result, this ratio cannot be negative. This has to be a positive value. Okay, it cannot be less than 0. This term, and based on this, and since this term has to be less than 1. Okay, because this term is positive, this term is positive, it means this term should be less than 1, this factor. Okay, so as a result, this epsilon is a value which will lie between 0 and 1. So when it is 0, it means sigma d square upon sigma t cap square upon sigma d square, this term is equal to 1. Okay, so 1 means that the output of the Wiener filter, which is the estimate of the desired response, so they are exactly same. Okay, so dn cap and dn, when they are same, their variance is same. As a result, your error is 0. So this is the best Wiener filter that you can have. Okay, which produces the output that is exactly same as the desired response. And the worst case is that if this is 0, so it means your epsilon is 1. So there is no match between the desired response and the estimate of the desired response. Okay, otherwise its value will lie between 0 and 1. So the more it is closer to 0, the better is the design of the Wiener filter. Okay, because in ideal case this should be 0. Okay, then you can evaluate this mean square error in another form, like suppose. So you have seen that J minimum mean square is the difference between sigma d square and sigma d cap square. Okay, the difference between the two variances. Okay, this is the variance of the desired response and this is the variance of its estimate. So if you find the difference between the two variants, you will get the minimum mean square value. Now this sigma d square you can compute it as, since d cap n is the estimate of the desired response or it is the output of filter, so you can write it as wok u of n minus k summation over k from 0 to minus 1. This is simply the output of the filter in terms of convolution. Okay, so this O is basically used suffix just to say that the filter is operating in the optimum condition. So the filter weights are optimum. Or you can write it in the form of a matrix, basically WOH into U of n. So now these are matrices, these are vectors. Okay, where WOH, this is basically like this. You have a row matrix or a row vector and a column vector. So it is 1 cross m and this is a m cross 1. So this is the column vector of the filter weights. So it is W0, W1, W2 and so on. And of course since it is it's okay, no, this will be like this, star star star. And the second matrix, which is a column vector, it is a matrix of this input samples u of n, u of n minus 1 and minus 2 up to u of n minus n plus 1. So if you multiply them, you will get this equation. So I have written in the compact form like this. It is basically nothing but the inner product between the filter weights and the input sequence, okay, which is the equation of convolution set. So if this is dn, what will be this sigma d cap square, the variance, that is the expected value of dn square or dn cap square, and you can write it as e of d cap n into star. Okay, so it will become e of, now d cap n is this, it is WOH into UN, and if you take it star conjugate of this, okay, so it will become UN H into WO. Okay, the transpose of this. Okay, see what it basically means, how I have written this equation. This was WOH into UN, it was basically like this. Okay, so W0 and K is 1, K0, it's a W00 into U of n. This was like this star. Then plus W01 into U of n minus 1, again star. Then plus W02 into U of n minus 2 star, and so on. This is D cap n. If you take its conjugate, so the conjugate of this, it will become W00 into U of n minus 1 star, then W01 into U of n minus 2 star, and so on. So in the form of a matrix, you can write it like this. Okay, so now this transpose, Hermitian transpose, will be on Un, and on W of these matrices there will be no star. Okay, and when you take the expectation of this, so since W0H and WOH matrices, these are matrices of scalars, so E operator will not apply on this, so you will write at WOH into U of N into UN H into W O. Okay, and this will become our correlation matrix R. So it will become WOH R into WO, and RWO is nothing but your P as per the Wiener filter Wiener-Hoof equations. Okay, so RW can be replaced with P, so you'll get sigma D square as D cap square as W0H into P. Okay, so this, therefore you can write the Ga minimum as sigma D square, the variance of the desired response, minus, in place of this estimate you can write it as WOHP. J minimum. Okay, or you can eliminate this dependence on this filter weights. Okay, so you can write it as further sigma D square minus P WOH, sorry, PH, and this W, and that will become sigma D square minus PH, and in place of W you can write the Wiener's filter solution, which is R inverse P. So this will be your, this is how you compute the minimum mean square error. Okay, so if you know the autocorrelation matrix and the cross correlation matrix and the variance of this desired response, you can find that what will be the minimum mean square value for the Wiener filter. Okay.